Alright, we're going to do a practice problem for sketching a curve for the function y equals 2x to the fifth plus 5x squared minus 1. I'm going to step you through the rules, and again, if you can go the whole distance, you can take a look at the end, make sure that you end up with the correct curve. First, you want to look for three things. You want to start with the initial function. Think, is it continuous? Is it a polynomial? So it is. What's the domain? The intercepts, and is it symmetric? Is it even, odd, or periodic? Try to answer those questions and then pause and go. But I'm going to keep going when I ask these questions. And first thing is we end up with that it's an element that domain's all reals. You plug in 0 for x. Obviously, the y-intercept's -1. The x-intercepts are hard to calculate, so I won't figure them out. And it is not even, it is not odd, and it's not periodic. So this means we're going to do quite a bit of work on this polynomial to graph it without a calculator. Next thing up typically is I want to know about, and there's no asymptotes then either, okay, because it's not a rational. So I want to next look for increasing and decreasing, max, mins, and concavity, which means I need derivatives. So I'm going to take the derivative and factor the derivatives. And again, an easy power rule problem, all right? And I haven't factored y prime prime. I'll do that here real quick. All right, I see critical points. Again, that's where f prime of x is 0 or doesn't exist. But again, polynomials doesn't exist. We have two critical points at 0 and -1. So we got that going on. And then I look here, and I'm really also interested about where f prime prime of x is equal to 0, possible point of inflection. And again, I can solve this portion for 0 right here. So the 10 doesn't matter. So I get -1/4 equals x cubed. So I get the cube root of -1/4. All right. So that value, is going to be a point we want on our table also. So I'm going to start with increasing, decreasing, roll into max and mins using the first derivative rule and the second derivative rule, and defining concavity. So I'm going to start making a table. We have x, f of x, f prime of x, f prime prime of x. And I'm going to have a section here where I do some notes, all right? I'll move that table down. I got a little sloppy here. All right. So I got 3 points in my table. I have -1 cube root of -1/4 and 0. And I know that the critical points are where the first derivative is 0. That's here and here. And I know this is where the second derivative is 0, possible point of inflection. All right, I'm going to actually figure out the signs using the factored one. So when I have a value to the left of -1, like -600, I plug it in here, I can immediately see that it's going to be positive. When I have a value between -1 and 0, like -0.5, and again, I can see that this is a negative, -0.5, so to make that negative, that's going to be a positive. If I plug -0.5 in there, it's going to be positive. So this is going to be a negative. It's negative times positive, positive. And then finally, I'm going to look to the, and again, not to be confused, it's negative all the way through here, all right? So it's negative here, and I can erase this line across so we see that's negative all the way in that interval. And finally, to the right of 0. And obviously, that you can tell from the first derivative that's going to be positive. Now, you can see sign changes across critical points. So you know that you're going to have max or min. So we're going to use the first derivative rule. All right? So by first derivative rule, all right, goes positive to negative. And again, I picture it in my head, positive and negative. I know that that is a local max. Likewise, down here by first derivative rule, it goes negative to positive. That means it's a local min. Now, the second derivative rule states if it is 0 at the first derivative, and at the max, it's going to be negative. So we can double check ourselves here, because that would be the second derivative rule, and make sure that at -1, the second derivative is negative. If you plug in -1 up here, you'll see that it is negative right here. I'm checking that function. Likewise, this has to be positive. If I plug in 0, you can see that this is positive. So we now have where it's increasing and decreasing in this area and decreasing in between. All right, and then we also know the concavity. It's concave down to the left of the cube root of -1/4, and it's concave up to the right. So I can make this curve now. I'm going to try to go dual page. And I'm going to make a graph over here on my new page. Cartesian coordinate system, we'll make it nice and big. Now, if I was interested in the values, I can take 1 second here, and I'll do it in red, and I can plug in -1 for the local max, and I can plug in 0. Now, 0 we already did. 0 was -1. That was one of our intercepts. That is also a local min. So 0, -1 is a point on our graph. If I plug -1 into the original function, -2 plus 5 is 3. 3 minus 1 is 2. I know the local max value at -1 is 2. And I know the point of inflection, because there is a sign change across the second derivative here, happens at this cube root of -1/4. So somewhere in here. So it is increasing from negative thing to -1, decreasing in between, and increasing out of here. Concave, I'll trace the concavity. Concave up to here, to -1/4, and then cube root of -1/4, and concave down there. And again, from the sine of the second derivative. All right? Fairly straightforward polynomial sketching without a calculator, using the first and second derivative rules. And again, just a real rough curve sketch. Just keep practicing.